Hello, I'm Professor Von Schmohawk, and welcome to YU. So far, we have introduced quadratic functions and quadratic equations. We have seen that the graph of a quadratic function of x is a parabola. And by setting that function equal to 0 and solving the resulting quadratic equation, we can find the values of x where the parabola intersects the x-axis. In other words, the parabola's x-intercepts. These values graphically correspond to the zeros or roots of the function. So let's take a look at the different ways that a quadratic function of x can intersect the x-axis. We'll start with the simplest quadratic function of x, x squared. Setting this function equal to 0 gives us the quadratic equation for this function. The only value of x which when squared is equal to 0 is 0. So the quadratic function x squared has a single x-intercept at the point where x equals 0. Now let's do the same thing with a slightly more complicated quadratic function, x squared minus 4. Setting this function equal to 0 gives us the quadratic equation x squared minus 4 equals 0, or x squared equals 4. There are two values of x which when squared are equal to 4, positive 2 and negative 2. These two solutions can be written as x equals plus or minus 2, which corresponds to the 2 points where the function's graph intersects the x-axis. So when the graph of a quadratic function of x intersects the x-axis, it can have either 1 or 2 x-intercepts, and thus 1 or 2 roots. It is also possible for a quadratic function of a real variable to have no roots. This situation occurs when its graph does not intersect the x-axis. However, this is true when only real numbers are considered. Several hundred years ago, a new type of number called an imaginary number was created by mathematicians specifically because of functions which have no real roots. When imaginary numbers and complex numbers, which include imaginary and real numbers, are included in our number system, it can be said that all quadratic functions have two roots, although these roots may or may not be real and may or may not be distinct. Later in these lectures, we will introduce imaginary and complex numbers and see how these numbers opened up a whole new world of mathematics. As we have just seen, solving a quadratic equation of the form x squared minus c equals 0 is easy, since as long as c has a positive value, this simply amounts to finding the square root of c. The same is true for equations of the form ax squared minus c equals 0, since if we divide the equation by a, we get the same type of equation as before, except that we take the square root of c over a instead of the square root of c. On the other hand, quadratic equations that include an x term can be more difficult to solve. There are a number of methods for solving quadratic equations like this. The methods we will examine in the next few lectures are based on the zero product property. So what exactly is the zero product property? Let's say that we have a number or expression which is the product of two or more factors. For example, let's assume that the product is composed of two factors which we will call a and b. The zero product property states that if any factor is equal to 0, then the product of those factors must also be 0. This same logic applies to the linear factors of a quadratic expression. As we showed in the lecture, creating quadratic expressions using the FOIL method, a quadratic expression can be created by multiplying two linear expressions together. Those linear expressions will therefore be factors of the resulting quadratic expression. So when x is a value that causes any factor of a quadratic expression to be 0, then the quadratic expression will also have a value of 0. This seems obvious since the product of anything multiplied by 0 must be 0. But the 0 property also states that the converse is true. If a product of factors is 0, then one or more of the factors must be 0. So every 0 of a quadratic function must also be a 0 of one or more of its linear factors. Therefore, we can find the zeros of a quadratic function by finding the zeros of the simpler linear functions that are its factors. This means that instead of having to solve a quadratic equation, we can solve linear equations, which are easier. So to find the zeros of a quadratic function, we factor it into linear functions and then identify the zeros of those functions. But is it always possible to factor a quadratic function into linear functions? If the quadratic's graph intersects the x-axis, the answer is yes. Although when there is only a single intersection point, the two linear factors will be identical. However, if we are only considering real numbers, it will not be possible to factor quadratic functions whose graph does not intersect the x-axis. But any quadratic function whose graph does intersect the x-axis, and therefore has real zeros, can always be factored into two real linear functions which may either be identical or distinct. So to factor a quadratic function, we must find a pair of linear expressions which, when multiplied together, produce the quadratic expression defining the function. Fortunately, there are several easily recognized cases of quadratic expressions called special products, whose factors can be readily identified. In the next two lectures, we will examine two kinds of special products, including quadratic expressions which are the difference of squares, and quadratic expressions which are perfect squares.